Hey guys, this is 12.3 inscribed angles. So last time we talked about central angles. Central angles are measured from the center of the circle. Inscribed angles are set on the circle, as you can see in the picture here. So here's the definition, verbal or word definition of an inscribed angle, but it's an angle with the vertex on the circle. And the intercepted arc is the arc the angle hits. So you can see that in the picture in blue there. So the angle is marked with a little arc in red there. The angle is made up of the two rays with the vertex on the circle. And the blue arc is the intercepted arc. And there's a special theorem about inscribed angles and intercepted arcs. And it says if an angle is inscribed in a circle, then its measure is half the measure of its intercepted arc. So for example, if you have an inscribed angle of 37 degrees, its intercepted arc would be double that, or 74 degrees. And if you're given an inscribed angle of 112 degrees, as we see in part B, that's half the measure of its arc, meaning its arc is double that, so it would be 224 degrees. And this one we have marked as a 90-degree angle, meaning its little points here and here, both here and here, if that's a 90, it intercepts an arc right here that has to be double that, or 180 degrees. So that's hitting the 2 points of the diameter right through here, as you can see. So big idea there is if you're given the inscribed angle, you double it to get the intercepted arc. If you're given the intercepted arc, you would take half of it to get the inscribed angle. So let's see how that works down here in example 2. So we've got 110 degree intercepted arc there. If I were to draw the arc, it's from here to here. It's supposed to be 110 degrees. But 110 degrees could be. And our inscribed angle would be half of that, or 55 degrees. In the next picture, we've got a dashed line going through the center of the circle, meaning that that must be the diameter. So half of the intersected arc AB would be, AB is 180, so it would have to be 90 degrees. All right, so suppose that AB is 72 degrees. So there's AB, it's 72 degrees. We're going to find the measure of ACB. ACB is right there, and angle ADB, which is right there. Both of those inscribed angles are congruent because they hit the endpoints of the same blue intercepted arc. And they will be exactly half of the intercepted arc. So half of 72 degrees is 36 degrees. So that means angle ACB is 36 degrees, and angle ADB is also 36 degrees. So that's working backwards with that same theorem. All right, theorem 1211 is a corollary. Corollary means a helper theorem, so it's a bonus theorem. Mathematicians are excited about corollaries because it's a theorem that we get for free based on the other theorem. So previous theorem 1210. So if it says if two inscribed angles of a circle intercept the same arc, like we saw in this example right here that we just did, then the angles are obviously congruent. So there you go, we got a corollary there. Oops, too far. All right. So inscribed polygon. An inscribed polygon is a polygon inside of a circle. It has all of its vertices inside the circle. Remember, a polygon is made up of straight lines. It's an enclosed shape of straight line segments made up in such a way that you cannot, if you were to continue the line segment through, they don't go through the interior of the shape. And so that's what a polygon is. So an inscribed polygon is a many-sided figure, straight line segments, enclosed figure inside of a circle. So you got a picture of one down here. That should be enough. It says if a right triangle is inscribed in a circle, so we saw this actually already. The right triangle is inscribed in a circle. There it is. Then the hypotenuse is a diameter of the circle. Conversely, so there's our right triangle there. Conversely, if one side of an inscribed triangle is a diameter, then the triangle is a right triangle. We saw examples like that previously here. If you go back, here's one here. Oh, and then I don't want to go for that far back here. And then we had one right here as well. So those are right triangles inscribed in a circle. All right, so it says quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So quadrilateral is a four-sided polygon. It can be inscribed in a circle if and only if its opposite angles, so opposite angles would be like these guys, E and P, or these guys, F and G, are supplementary, or in other words, add up to 180 degrees. So now we're going to use those little theorems or corollaries to theorem 1211 to find the value of the variables in the following diagram. So here we have a triangle inscribed in a circle. We're given one of the degree measures. We know that x has to be 90 degrees. And combine that with the fact that we know that the three angles must add up to 180. 90 and 40 give us 130 degrees, leaving 50 degrees for angle Y. Over here on B, it says the only way you can have a quadrilateral inscribed in a circle is if the opposite angles add up to 180. So that would mean x has to be 80 degrees, so that these two add up to 180. And 3y plus 120 have to equal 180. You could use a little trial and error or do some algebra here and solve for y to figure out what y is. Subtract 120 from each side, 3y equals 60, divide by 3, y is equal to 20. So y equals 20 in this case. And that angle would then be, of course, 60 degrees. You could have said it that way. You could have said 3y equals 60 degrees and then divided each side by 3 to get the 20 degrees. That would have worked as well. But the opposite angles of that quadrilateral must add up to 180 degrees. I got one more down here. Involves a little more algebra. We know that 2y plus 5x must equal 180, and we also know that, so these two are opposite, 3x plus 3y must equal 180. So this is going to force our hand a bit. This is forcing us to do some algebra here. So we've used the geometric definition, which is a big theme in geometry, to create an algebra equation, a system of equations here to solve. Now, as I look at this, I've got y's and x's above and below each other in both cases, so we need to line up the x's and y's. So we're going to rewrite this equation like this. We've got 5x plus 2y equals 180, and then we've got 3x plus 3y equals 180. And I'm still looking at this and seeing that I am going to have to multiply both equations by something to be able to eliminate a variable. I'm going to use elimination method on this because they're both in standard form. But yeah, 3 does not go into 5 evenly. It's not a common factor there, and nor does 2 go into 3 evenly. So we're going to have to multiply both equations by something. One of them will have to be negative. So I'm going to take the following approach here. I'm going to take the first equation, the 5x plus 2y equals 180. I'm going to multiply each side. I think what I'll do is eliminate, we'll just eliminate x. It'll be fine. You could eliminate x or y, but I'm going to multiply that through by something, and then I'm going to multiply the 3x plus 3y equals 180 through by something. The lowest common multiple between 3 and 5 would be 15. First of all, I said 3 doesn't go into 5, so you got to go ahead and double 5. 3 doesn't go into 10, so that won't work. Triple 5, you get 15. 3 does go into 15, so I've got to get a 15 in front of the x. One of them must be positive, one of them negative for this to work. So I'm going to multiply through the first equation, each side by 3, and the second equation, each side by negative 5. And that will give us two new but equivalent equations. So new top equation is 15x plus 6y. I get that by distributing the 3 equals 540. And the second equation is negative 15x minus 15y equals negative 900. Put a line underneath them. X is eliminated when I add. I get negative 9y equals negative And this will be 360. Because I have a negative on each side, I can divide each side by negative 9, and I get a y value of positive 40. So I found the y variable here. Y is equal to 40. So if I put a 40 in for y up here, this angle would be 80 degrees. This angle would be 120. This angle up here would be 120 if I put 40 in for y. So, different ways you could do this. You can go finish your algebra over here for your system, plug in 40 into one of the original equations. I could plug in 40 up here, take 3x plus 3 times 40 equals 180. That's one way to do this. 3x plus 120 equals 180. Subtract 120 from each side. So 3x equals 60. Divide by 3. X equals 20. So that would be one way. That's my x. Another way would be to say, okay, I know that 3x has to equal 60, which I saw in my algebra right here, because these two angles here and here that are opposite each other in that quadrilateral must add up to 180. So if this is 120 already, this 3x right here must equal 60. And so you could start at 3x equals 60. X, therefore, has to equal 20. All right, so that one involves a lot of algebra. So be prepared for that as you're going through the problems. All right, theorem 1212, it says if a tangent and a chord intersect at a point on a circle, that's this point right here, then the measures of each angle formed is 1/2 the measure of its intercepted arc. So it's kind of similar to our inscribed angle theorem. And so what it's saying is that measure of angle 1 is equal to 1/2 of measure of arc AB. So angle 1 is 1/2 of this green arc, and measure of angle 2 is 1/2 of that blue arc I just drew. So we're going to use that theorem to find the measures of some of these arcs. So here I have an intercepted arc of 150. I really just see this as similar to the inscribed angle. So x here is equal to 1/2 of that, which would be 75 degrees. So x right here, that angle is 75 degrees, which is 1/2 of that 150 degree arc. Going the other direction, if I want to find measure of arc RSP, it should be going this way, and that angle given where the tangent line meets the chord is 130, so a measure of arc RSP would be double that, or 260. So it's going in the other direction. In this part C, it says ABC, so angle ABC, that's this guy right here, is 64 degrees. Measure of arc ADB, that's this guy right here, is 4x plus 10. And so we're going to find x. So first of all, I know that AC, let me draw AC here, has to be double the 64, which is 128 degrees. I can then take the 4x plus 10, which represents this arc right here, and set it equal to whatever the degree measure of that red arc is. Well, how do I find the degree measure of that red arc? Well, if I know AB, the blue arc, is 128, I can find the red arc by taking 360 minus 128. So 360 minus 128 is going to be 200, let's see, 130, 230, 330, so 232 degrees. And I can set that 232 degrees equal to the 4x plus 10 and use that to solve for x. So subtract 10 over, this is 222 equals 4x. Divide by 4, so x equals, it goes into 25 times. 2 left over goes into 22. 5 times, and we got 55.5, I believe, is what x is equal to. 220, yeah, 222. So that's it. Hope this helps you out. All right, we